Welcome to the Deep Dive, where we peel back the layers on the objects we interact with every single day but, rarely think about. The silent workhorses of our modern world. Today, we're taking a deep, really detailed look at a piece of hardware that is it's absolutely fundamental to the structure of the European home. We are talking about the chipboard screw.
It's one of those things, isn't it? It's the fastener that everyone assumes is simple. But as you said, we have a whole stack of sources here. Everything from metallurgical reports to some very specific design standards.
Yes.
And they all prove it's a marvel of specialized engineering. I mean, if you've ever wrestled with flat pack furniture, you know this screw.
Oh, I know it well.
But you almost certainly don't know the extraordinary effort that went into designing it.
Exactly. You came to us with this genuine curiosity about this tiny, often overlooked component. So our mission today is to take that whole pile of specs and market data and turn it into a truly comprehensive guide.
Yeah, let's do it.
We're going to cover the chipboard screw's very specific anatomy, the complex metallurgy that allows it to self-tap without snapping, and its critical position in the massive European fastener economy. And here is the core takeaway, really, the absolute mission statement for this deep dive. The chipboard screw is not a standard wood screw.
Not at all.
It is purpose-built. It has to be optimized for materials like chipboard and MDF, that's medium-density fiberboard, which are, and this is key, significantly denser, harder, and just fundamentally more brittle than natural softwood or even hardwood.
I think that right there, that's the first aha moment for a lot of people.
Yeah.
Why is that density so critical? I mean, when I'm working with pine, I can usually just ram a square in and the wood fibers just sort of compress.
They do.
What happens when I try that with a sheet of MDF?
You introduce two massive risks, basically at the same time. First, that high density means the screw has to cut its path really aggressively. That leads to immense friction and a lot of driving torque.
So if your screw isn't hardened correctly, the head just snaps right off. Or the little recess for your driver bit just strips out immediately.
I've had that happen. It's incredibly frustrating.
It is. And the second risk is that because these materials are fibrous and they're bonded with resin, they lack the forgiving internal structure of solid wood. They're brittle.
Right.
So if the screw tip wedges its way in instead of cleanly cutting, you get a catastrophic splitting of the panel. And this almost always happens near the edges, which is, of course, where most of your joints are made.
So using a cheap, standard wood screw in chipboard, it's a recipe for disaster. Not just in terms of, immediate strength, but for the structural longevity of the piece.
Exactly. You're going to script those threads out instantly.
Which leads to a joint that fails the moment any real load is applied to it.
Precisely. The strength of that joint relies entirely on the successful engagement of the threads in that dense fibrous core. A standard screw's threads are just too shallow, and its whole geometry is wrong for the material. It ends up deforming the material rather than forming clean threads inside it.
And to really appreciate the innovation that's baked into this little piece of metal, we need to understand the sheer economic engine that it serves. We're talking about the European fastener market, and it is a behemoth.
It truly is. Our sources indicate that the entire European industrial fasteners market, it's valued at approximately 23 billion euros. For 2024.
23 billion.
We are not talking about a niche industry here, and the chipboard screw is right at the core of this figure.
Why is that?
Primarily because it's tied directly to the explosion of the ready-to-assemble the RTA furniture industry, popularized globally by companies like IKEA.
That RTA market, it demands consistency at just an astonishing scale. I mean, every year, millions upon millions of these screws are packaged into those flat pack boxes. And the screw, it can't be slow to drive, it can't require you to pre-drill a hole, and it absolutely cannot fail in the hands of a consumer with a cheap screwdriver or, a moderately powerful impact driver.
And that's it, that need for consumer-friendly, high-volume reliability. That's what drives all the engineering decisions we are about to unpack. The market needs fasteners that balance low cost with exceptional performance, ease of use, and guaranteed joint integrity for decades.
And this is why the metallurgy, specifically that C10B21 steel we're going to get into later, is so critical to this segment of that 23 billion market.
Absolutely critical.
Okay, so let's establish where this screw truly reigns supreme. We've said it's a specialist, not a generalist.
It is the workhorse for engineered wood. That's the best way to think about it. While a traditional screw can handle solid wood, the chipboard screw is optimized specifically for the structural limitations and also the benefits of wood composites.
So particle board, chipboard, MDF.
All of them.
And the primary stage for this workhorse has to be furniture assembly.
Absolutely. Just think about the construction of a typical kitchen cabinet or a wardrobe. You have these panels joined at 90-degree angles.
Right.
You need a fastener that can distribute the load, pull the panels together tightly without splitting the material, and resist the constant stresses of, opening and closing doors and supporting whatever you put on the shelves.
Cabinet making is arguably the cornerstone application then.
Yeah.
It demands a screw that maximizes holding power within the material's cross-section. But we need to be really clear about distinguishing it from its cousins in the self-tapping family.
That's a great point.
I think a lot of DIYers, they just assume a screw's a screw, especially if it's black or has deep threads.
That is a very dangerous assumption. Take the drywall screw, for instance. It has a similar look, often has a black phosphate coating coarse thread.
Yeah, they look alike.
But its design is completely different. The bugle head of a drywall screw is designed to compress the paper face of the gypsum board without tearing it. It lets the screw head sink just below the surface so you can apply filler and get a smooth finish.
And the threads on that drywall screw, while they're coarse, they're really engineered for the relatively soft gypsum and maybe some thin steel or softwood studs behind it?
Precisely. They're optimized for speed and just holding plasterboard in place, not for high pull-out resistance in something as dense as particle board. The standards in Europe actually reflect this. Drywall screws are governed by standards like EN 14566.
Okay.
The chipboard screw, on the other hand, it has to contend with that much higher internal density and brittleness of the composite materials. So it's designed for maximum material engagement, which requires those really specific, deep, coarse threads that aggressively cut the fibers rather than just parting them.
This brings us right back to the fundamental design requirements dictated by the material itself. We know MDF and chipboard are significantly harder.
Yeah.
But there's another factor here, isn't there? The thickness.
Thickness is absolutely key. RTA furniture often uses 15 millimeter or maybe 18 millimeter panels. So when you're fastening through the face of one panel into the edge of another, your working area is tiny.
Really tiny.
And if that screw pushes material outward, you split the edge. Game over. If the screw can't reliably tap its own thread, then the manufacturer or the consumer has to pre-drill.
And pre-drilling is a huge time sink in volume manufacturing. And it's a massive point of friction, a pain point for the consumer at home.
A huge one.
So the coarse threads aren't just for grip. They're also for aggressive material clearance and fast, reliable driving.
Yes. The thread pitch is maximized to allow the screw to advance really rapidly with each turn, and that translates directly to efficiency on the assembly line and, of course, less effort for the DIYer.
It's physics, really.
It is. Think about it. Fast driving requires low torque for a high-pitched thread. Low torque prevents you from shearing the screw head off.
Right.
But you still need massive pull-out resistance. The only way to square that circle is by having threads that are incredibly deep to maximize surface contact and a point that is incredibly sharp, ensuring a clean cut every single time.
And that's where the specific material science of the steel comes in, making sure the cutting edge of that thread stays sharp despite all that resistance.
That's the magic.
Okay, let's unpack this marvel of microengineering, detail by detail. And let's start at the top, the interface between the tool and the fastener.
Right, the head. The chipboard screw's head is probably its most recognizable feature after its thread profile. We almost always see a countersunk head, or CSK head.
And that's for a very specific reason.
Purely aesthetic and practical. It ensures a perfectly flush finish, which is essential for furniture construction where all your surfaces need to be clean and flat.
And I've noticed that compared to standard wood screws, the head on a chipboard screw often seems noticeably wider. You mentioned load distribution before, but what's the practical implication of that wider diameter?
It's so important. When you drive a screw into the edge of an 18 millimeter chipboard panel, you're putting immense pressure right near the weakest point of that material. That wider head surface area spreads the clamping load over a larger footprint. It prevents the screw head itself from crushing the material or starting a split right at the surface layer. It's basically a protection mechanism for the material.
And then, underneath the head, we find this fascinating feature. The nibs or ribs, what are those for?
The nibs are truly specialized. They're these small ridges or flutes just beneath the countersunk part of the head. They serve as milling cutters.
So they're actually cutting the material.
They are. As the screw is driven that final turn, these nibs engage the top surface, which is often a thin veneer or melamine or laminate, and they aggressively chew away that material so that the CSK head can seat cleanly and perfectly flush.
So without the nibs, you'd just be relying on the wedging action of the head, which would probably crush that decorative layer, leading to splintering or a messy finish.
Exactly. The nibs essentially guarantee a professional, clean countersink every time, even if the material is something highly abrasive like melamine. It's a design feature that's optimized entirely for the aesthetics and the ease of RTA assembly.
And while we're talking about the head, we have to discuss the drive type. Traditionally, chipboard screws use the POTSI drive system, PZ.
That's right.
But increasingly, especially in high-performance or professional-grade fasteners, we're seeing a shift toward Torx, or TX, drive systems.
It's a very clear trend.
What's driving that shift, particularly in the European context?
Two things: torque transfer and cam-out resistance. The Torx drive system has 6 points of contact and a 90-degree flank angle. This provides just superior engagement compared to the shallower recesses of a POTSI drive.
And what does that mean for the person using it?
It means when you're using a powerful impact driver, which is standard on assembly lines and more common for DIYers, the Torx system virtually eliminates cam-out.
And cam-out is when the driver bit slips out of the screw head, right?
Exactly. It slips out, often stripping the head and damaging the bit at the same time.
So reducing cam-out is crucial, not just for speed, but for the longevity of your components. A stripped screw head means wasted time and potentially a ruined piece of furniture.
It does. Torx is fundamentally a more resilient system for high-torque applications, no question.
Okay, moving down the screw, let's get back to the thread itself. The deep, coarse threads are crucial, but you said the cutting action must be flawless. This is where the specialized cutting tips come in.
Yes, this is where you see some really clever engineering, fulfilling the need for advanced self-tapping features.
A lot of these screws incorporate what's called a serrated thread or a cutting flute. Tell us about the serration first.
The serrated thread usually involves small, sharp notches that are ground or formed into the leading edge of the threads, right near the tip. This creates a miniature sawing action.
Like little teeth.
Exactly like little teeth. As the screw rotates, these serrations decrease the initial resistance and they efficiently cut the wood fibers, rather than just forcing them apart. This significantly lowers the amount of driving torque you need just to get the screw started.
And the cutting flute. This is similar to the concept of the Type 17 point, isn't it?
It's the exact same principle. A cutting flute is a small notch or a groove near the very tip of the screw. Its purpose is to evacuate the material chips that are created as the screw taps its thread. You can think of it like the flute on a drill bit, which carries away the swarf.
And managing that waste, the wood chips and fibers, is critical because if that material compacts at the tip, it causes wedging.
And wedging results in the panel splitting.
So that Type 17 point concept, that sharp, relieved cutting edge, even though it's often associated with deck screws for hard timber.
It's the identical principle, just applied to high-performance chipboard screws. It ensures a clean, low-resistance entry into these dense materials. This is what allows manufacturers to reliably say on the box that no pilot hole is necessary.
Now let's integrate the specific European standard that governs all these characteristics, DIN 7505.
Yes.
This standard defines the requirements for tapping screws for chipboard. We should probably look at the crucial subtypes, A, B, and C.
We should. DIN 7505 is the central reference point for these fasteners. And the subtypes, they generally delineate the primary geometry, often the head type, which is crucial for different applications in furniture and construction.
So let's start with DIN 7505A.
That's your classic, your essential countersunk head chipboard screw. It defines the geometry needed for that flush finish we talked about, essential for internal panel construction and any decorative surfaces. It is, by far, the most common type used in RTA furniture.
The one everyone knows? And DIN 7505B.
This usually refers to a variation with a pan head or a round head. This is used when the screw head needs to bear down onto a surface but doesn't need to be countersunk, for instance, when you're fastening thin metal fittings onto chipboard. In that case, maximizing the bearing surface under the head is more important than the aesthetics of a flush finish.
Got it. And finally, DIN 7505C.
This often specifies the larger, more heavy-duty applications. Sometimes it incorporates a hexagon washer head or a specific type of flange head.
So more structural.
Exactly. These are designed for structural applications in construction or heavy cabinet making where you need maximum torque and robust pull-through resistance rather than just a clean finish. The head geometry here is all about high clamping force.
So those letter designators tell us immediately what the screw is meant to do. A for aesthetics and flush finishing, B for utility fastening, and C for high torque structural clamping.
Precisely. And let's go back to the thread length for a moment, because this is another thing that differentiates it from, say, structural wood screws. Chipboard screws are almost always fully threaded.
Meaning the thread runs right up to the underside of the head.
All the way up.
So why abandon the smooth shank, which is so critical for pulling two pieces of solid wood tightly together?
Because the game changes when the material is weak. In solid wood, that smooth shank acts as a clamping mechanism. It spins freely in the top board and pulls it tight. In chipboard, the material's internal cohesion is very low. So if you rely on the friction of a smooth shank to pull that top panel, you risk the wood fibers tearing and the material bulging or separating before the head even fully seats.
I can picture that.
So by making the screw fully threaded, you maximize the thread engagement surface area. You distribute the holding force along the entire length of the screw that's embedded in that low-density core.
So it's a pragmatic trade-off. You're sacrificing some of that ultimate clamping force in exchange for a massive increase in pull-out resistance and a reduced risk of stripping the material during insertion.
You've got it. The holding power in chipboard depends almost entirely on the volume of thread engaged with the material.
All right, so if the anatomy is the visible engineering, the metallurgy is this invisible insurance policy. We need a screw that's hard enough to cut this dense material, but tough enough not to shatter or shear when you hit it with a power driver.
This is where we move into the really fascinating world of carbon steel wire. Chipboard screws are generally made from low-carbon steel wires that are suitable for cold forming, and we're going to focus on two dominant grades, C1022 and C10B21.
Before we get into the difference between them, let's talk about the manufacturing process. The screw isn't melted and cast into shape. It's created through mechanical deformation, specifically cold heading and thread rolling. Why is that so critical?
Cold forming is absolutely essential for strength. In cold heading, the steel wire is pounded or compressed at room temperature to form the head and the point. This mechanical process, it work hardens the material.
Okay.
But even more important is thread rolling. Instead of cutting the threads with something like a lathe, which would interrupt the grain structure of the steel.
You're cutting into the grain.
Right. Instead, the threads are formed by pressing the screw blank between two very hard dies.
So you're displacing the metal, not removing it.
Exactly. And this displacement forces the grain structure of the steel to follow the contour of the thread. This flow line significantly increases the fatigue resistance and the strength of the threads, making them much less likely to strip or shear when they're subjected to immense torque. It's an optimization for maximum fatigue resistance.
So we start with C10022 and C10B21. Both are soft and ductile enough to be cold formed. Both are excellent starting points. But the divergence happens in the heat treatment.
Yes, the quenching and tempering process, the Q&T process, that's the moment of truth. This treatment transforms that soft steel into the incredibly hard material needed to self-tap.
How does that work?
The C1022 and C10B21 wires are heated until the microstructure changes, it's called austenitizing, and then they're rapidly cooled or quenched to lock in the hardness, specifically a microstructure called martensite.
That sounds incredibly technical.
Huh.
In layman's terms, what is martensite and why do we want it?
Martensite is the hardest but also the most brittle phase of steel. You can think of it as crystallizing the carbon within the iron structure under immense stress. So quenching creates this brittle hardness, and then the screw undergoes tempering, which is reheating it slightly, to regain a little bit of elasticity or toughness to prevent it from shattering.
So the Q&T process is this delicate balance. You want maximum hardness for cutting, but just enough toughness to resist the shear forces of installation.
It's a very fine line.
Now let's get to the showdown. What is the fundamental difference in the chemistry of C2022 versus C10B21 that dictates their final performance after this Q&T process?
The difference is one tiny element, boron. C10B21 contains a minute, very specific addition of boron, often less than 0.005%.
That's a tiny amount.
Tiny. But this tiny addition is a complete game changer because of what we call the boron effect.
Okay, what mystical power does boron wield inside that furnace?
It grants C10B21 exceptional hardenability, and hardenability refers to the depth to which the steel can be effectively hardened during quenching.
I see.
C1022 is typically suitable for case hardening. This is where the surface layer gets very hard, which is perfect for cutting, but the core remains relatively soft and tough, or ductile. This works perfectly well for many standard chipboard screws.
But the specialist, C10B21, allows for what's called through hardening.
Exactly. The boron slows down the transformation of the steel during cooling, and that allows the hard martensitic structure to form much more deeply or even uniformly right across the entire cross-section of the screw.
So that means C10B21 screws have a higher, more consistent core hardness and tensile strength throughout the entire body of the screw.
That's right. So C10B21 is the choice when you need maximum resilience, when the screw is expected to handle the extreme torque of high-speed power tools, tap into exceptionally dense materials, and achieve the highest possible shear strength, sometimes comparable to grade 8.8 bolts.
And this is a direct financial decision for the manufacturer.
Oh, absolutely. If a supplier is producing screws for a mass-market RTA company, they have to guarantee reliability. A C10B21 screw costs more initially, but it virtually eliminates expensive customer complaints about broken screws or assembly failure. It's an investment in product integrity and reduced liability.
So C1022 is the cost-effective workhorse.
And C10B21 is the specialist, engineered for maximum consistent performance under stress.
Okay, so even with the toughest boron-enhanced steel, exposure to air and moisture is going to lead to corrosion. We need to talk about the armor, the coatings that protect these fasteners, especially given their wide range of applications, from dry interiors to maybe damp storage units.
Right. The primary armor for chipboard screws, intended for indoor furniture and general applications, is zinc plating. It's applied via electroplating, and it's the least expensive and most common surface treatment.
This gives us that classic shiny finish we see in the hardware aisle. But there are crucial visual distinctions in zinc plating that indicate different levels of protection, right?
Yeah.
We often see clear or blue zinc and also yellow zinc.
That's a vital point to make. The clear or blue zinc is zinc-plated, and then it's typically passivated with a thin chromate layer. This is the basic aesthetic finish. It provides mild protection. It's ideal for dry interior environments.
And the yellow chromate finish, it looks different, more iridescent.
That yellow iridescent color signals a thicker or a multi-layered chromate passivation process that's applied over the zinc. Historically, this offered superior corrosion resistance compared to the blue or clear finish, though modern chrome-free passivates are closing that gap.
So the yellow appearance usually suggests a slightly higher expectation of mild, damp exposure, but still firmly within indoor parameter.
That's a good way to put it.
So in the context of the ISO corrosion classifications, these standard zinc-plated fasteners, whether they're clear or yellow, they're pretty limited.
Oh, very. They are restricted to C1, which is very low, or C2, which is low, environments. This means heated, controlled indoor spaces. A C1 environment is a heated office. A C2 environment might be an unheated warehouse, or maybe a room where condensation occurs occasionally.
And if you put that basic zinc screw in a coastal area, or just expose it to rain,
It will fail, and it will fail rapidly. You'll get those familiar reddish-brown streaks of rust bleeding onto your composite material.
so for anything approaching structural use or outdoor applications, you have to escalate the coating.
Absolutely. Moving into C3, or medium environments, like a sheltered outdoor area or a damp basement, we start looking at more advanced systems. Often ceramic hybrid coatings, things like Rustbird or Dacrymed or thick zinc flake systems. These multi-layer barrier coatings can provide hundreds or even 1,000 hours of salt spray resistance. They offer genuine long-term protection.
Now let's just consolidate the regulatory environment here. We've established that fasteners in Europe operate within a really rigorous framework of EN and ISO standards. We already touched on DIN 7505 for the product itself.
We did. DIN 7505 governs the specific dimensions, threads, and features of the chipboard screw, but the material and the coating standards are just as important for quality control.
So for the mechanical properties of that specialized steel, we're relying on ISO 8981.
Correct. That standard ensures that the screw, regardless of whether it's C22-2 or C10B21, achieves the minimum specified tensile strength and hardness after that Q&T treatment. The manufacturer has to verify that the heat treatment process was successful.
And for the finishes we just discussed, the standards are just as clear.
Yes. ISO 40042 is the central standard for electroplated coating systems. It specifies the requirements for the thickness, the adhesion, and the subsequent treatment, like the chromate passivation passivation of zinc coatings.
So compliance here ensures the buyer gets the expected level of mild corrosion resistance.
Exactly. This whole ecosystem of standards guarantees that when a customer buys a DITV 505A screw, they know exactly what they're getting in terms of material, geometry, and surface protection.
This entire section really reinforces that the chipboard screw is a highly regulated, performance-driven product. It's so far from the generic screw that many of us assume it to be. So we've completed our ultimate guide to the chipboard screw. We started with what seems like a humble component, and we've exposed the complex engineering required to hold together millions of pieces of furniture worldwide.
Our journey really showed that the screw's specialized identity is defined by its ability to self-tap flawlessly into dense materials. And that's thanks to features like the nibs, the cutting flutes, and of course those deep, coarse threads.
We know the differences now between the aesthetics-focused DIN 7505A and the more structural 7505C variants.
And we understand the critical choice in raw materials. You have C1SO22, which offers cost-effective case hardening, while the high-performance C10B21, using the boron effect, delivers that superior, reliable core hardness for high-torque assembly. It's insurance against breakage.
And finally, we learned that coating colors actually matter. Your basic clear zinc is fine for the dry indoor C1 environment of your home.
But anything remotely damp demands a serious upgrade, or rust will quickly compromise the integrity of the joint and stain the material.
So we know the engineering, we know the standards, we know the market scale. But the story of the chipboard screw is about to get a lot more expensive. And for reasons completely divorced from the material itself, it is now on the front lines of global climate policy.
That is the ultimate essential context for this deep dive. The European Union's Carbon Border Adjustment Mechanism, or CBAM, is about to fundamentally reshape the economics of imported carbon steel fasteners.
Okay, so CBAM is effectively a carbon tax, but it's applied to imports of carbon-intensive materials like steel, aluminum, cement.
That's right. The aim is to prevent carbon leakage, which is where European manufacturers might move production to countries with weaker climate policies to save money.
And since virtually all of our carbon steel fasteners, that C2022 and C10B21 wire, are imported from outside the EU, this mechanism hits the fastener market directly and hard.
It does. Starting in 2026, importers will have to purchase CBAM certificates that correspond to the embedded greenhouse gas emissions of those imported screws.
Let's ground this in a practical example. Imagine a large European furniture manufacturer imports a container ship full of millions of fully threaded C10B21 screws from Asia.
Okay, that ship arrives at the port of Rotterdam or Antwerp. Before those screws can even enter the EU market, the importer has to account for the carbon used throughout the entire supply chain.
The entire chain.
Everything, from the energy used to smelt the raw iron ore into steel, to the electricity used in the wire drawing and the heat treatment, that austenitizing and tempering where the martensite structure was created. All of it.
So if the Asian manufacturer used a traditional high carbon intensity blast furnace process to create that steel wire, the embedded emissions are high.
Correct. And that means the importer will be required to buy a large number of CBAM certificates, which directly raises the cost of that box of screws.
But conversely, if the foreign supplier used cleaner energy sources or maybe a low-carbon electric arc furnace process, the cost of CBAM compliance would be significantly lower.
Much lower. This essentially forces European buyers to prioritize fasteners manufactured in greener jurisdictions or to pay a substantial premium for highly polluting imports. The price of the humble chipboard screw is now factoring in the global cost of carbon emissions.
It's the ultimate convergence of microengineering and macro policy. The next time you open that flat pack box, you won't just be checking the price or if it's clear or yellow zinc plated.
You'll be indirectly paying for the energy used in the furnace where that C10B21 wire was made. The chipboard screw, the backbone of RTA furniture, is now on the front lines of global climate policy and carbon cost accounting. Think about that engineering and that carbon footprint the next time you hear that satisfying whir of a Torx driver seating one of these unsung heroes.